All right. Assalamualaikum warahmatullahi wabarakatuh. So I will continue with the next chapter, which is chapter 4. All right. So for this topic, it would be about data link layer. Okay, and one of the main functions is as a data flow control. So I will introduce about this layer and the link layer addressing, flow control, error control, and then stop and wait ARQ, go back and ARQ, and selective repeat ARQ. All right. So for this, okay. So in a data link layer, all right. So what are the purpose of data link layer? Is that okay? So data link layer is a layer in between the physical and network layer, right? So it provides services to the network layer, and also it receives services from the down layer, which is the physical layer. So the scope of data link layer is that it is responsible in a node-to-node delivery. Okay, so node-to-node delivery. So and then it has to encapsulate the packet or the datagram received from the network layer into a frame, and then decapsulate back again the datagram into the frame. So it only need to encapsulate and decapsulate, but in between of the intermediate node, they also needs to do this process also. Okay, so the reason is that for each of the link in between the nodes, they may use a different protocol, okay, with a different frame format. Okay, so even if they are using the same protocol, encapsulation and decapsulation is needed because the link layer addresses that is needed to send out to another device would need to be changed. Okay, and then another major services or first services that is needed is that they provide the framing, where they framing means that the data link layer would need to encapsulate the datagram in a frame before sending it out to the next node. And then also responsible in the flow control, where um we before we can analogous it, we can define it like a producer and consumer. Okay, so as a producer, they would produce the item, okay, that cannot be so when they produce it, if the producer produce the items that cannot be consumed, accumulation of items would occur. Okay, so the sending data link at the end of a link is a producer of frames, and then the receiver of that data link layer at the other end is what we call as a consumer. Okay, so let's say the sender sends the frames and then at a different or much more higher speed compared to the receiver. What will happen is that they have like a congestion because of they cannot match to that speed. So the we cannot have, okay, like we can have two options. Okay, first is that to let the receiver of the data link layer, the data link layer of the receiver to drop the frames when the buffer is full. Okay, so let's say the buffer is full at the receiver, then and they cannot process it because of the speed of the other sender, right? So they would drop it. So that's the first choice. But for the second choice is that to let the receiver send the feedback to the sending data link layer to ask the sender to stop, okay, or to slow down, okay, to slow down the speed of sending the frames. So this is what it means as a flow control. As for error control, a frame in the data link layer needs to be changed to bits and transformed into electromagnetic signals, right, on the physical layer. So when they are transmitted through the transmission media, some of the signals, okay, would be susceptible or change a little bit. So when the receiver receive it, okay, it would need to be checked if the frame contain error. So the error needs first to be detected, and then after the detection, they need to be corrected, either corrected or discard that frame and request for retransmission by the sender. So since error detection and correction is an issue in every layer, so usually the error correction and detection is actually for involved in all layers. Okay. So and then other services is congestion control, where although a link may be congested with frames, which may result in frame loss, most data link layer protocol do not directly use a congestion control to alleviate congestions, although some wide area networks do. So in general, congestion control is considered an issue in the network layer or the transport layer because of its end-to-end nature. Okay. Um, Okay, so to better understand the functionality of the services provided by the link layer, we can divide the data link layer into two. Okay, one is data link control sublayer or DLC, and then another is MAC address control sublayer. So this is not unusual because we can see the LAN or Ethernet protocols usually use the same strategy. So the data link layer control, this sublayer, the first the DLC sublayer, deals with all issues common to both point-to-point and broadcast link. And then the media access control sublayer deals only with issues specific to broadcast link. Okay, so data link control can deals with issues in a point-to-point and also a broadcast. But media access control deals only in a broadcast links. Okay, so the media access control deals with issues specific to broadcast link, where in this case we separate these two types link at the data link layer. Okay, in the data link layer, okay, as I have mentioned before, they are dealing with the flow control and error control. And the main function is as a node-to-node delivery. So how do they deliver to the next node? We are using link layer addressing. So link layer addressing, or in this case, we are using a MAC address. Okay. So remember, on the network layer, we are using an IP address, right? So the IP address doesn't change, okay, at during the transmission, but the link layer addressing will change after it arrives to the next node. So I would like to introduce the type of link layer addressing. So it can be a unicast, multicast, and broadcast. But actually, IP address also have these three types. Okay, but for a link layer, they have specific or like a patterns. Okay. So for unicast, okay, look at the red font here. Okay, so to determine it is a unicast, it has a digit 3 at the second hexadecimal numbers on the first octet. And then for a multicast, remember, multicast is like a one to many, okay, one to many also. The same as but broadcast, but actually specific to a certain group. Okay, so to determine the difference group, they use two. The second octet of the second hexa of the first octet is two to specify the multicast addressing. And then if it's a broadcast, they use all one. Okay, FFFFF as a broadcast address. Okay, for flow control, it will tell sender how much data can be sent. And then it must wait acknowledgement from the receiver before send more data. So the flow data should not overwhelm the receiver. So the receiver will use a buffer as a temporary memory to store data before being processed. Okay. Error control. In this case, will be on the next subchapter. Okay, which is error detection and corrections, where the responsibility is that first to detect error. Okay, and then allows the receiver to inform the sender or lost or damaged frame. So if error is detected, then receiver needs to inform the sender if the frame is lost or damaged, and then to coordinate the retransmission. So in this case, we use automatic repeat requests, where anytime error happens, the specified frame would need to be retransmitted. Okay, so for flow control, okay, for the flow control of the retransmission, okay, we can use these three basics mechanism: stop and wait ARQ, go back and ARQ, and selective repeat ARQ. The stop and wait ARQ is the most basic method or mechanism, okay, where for each frame, it will be needed to send out. Okay, so frame 0 is referring to the first frame. Okay, and then when it's received by the receiver, receiver would check if it's okay, it's no damage on the frame, then it would acknowledge it. So the features of this flow control is that they must have some acknowledgement that the frame has successfully and then without error received. After that, the acknowledgement must be received by the sender to ensure that the next frame can be sent out. Okay, so when it receives acknowledgement one, ACK1, it means that the previous frame, which is frame 0, okay, has successfully received. So when it says 1, it means that to tell previous has been received. Now I expect you to send me the next one. Okay, so frame 1 would be sent out. So in this case, after the receiver acknowledge that frame 0 has been received, then the next one it will expect it would be R is equal to 1, which is a frame 1. So when it received the frame 1, okay, so and then there's no error, it will send out the ACK0. Okay, so that would be the normal operation. Okay, but remember, the media can have some interference and some lost packets and everything. So we need to consider certain situation. So for example, if it's a lost frame. So last frame, for example, frame 0 is normal. Receiver receive it. R is equal 0 and then it send ACK1. And then when the sender send frame 1, okay, it would expect that it would receive ACK0. Okay. So there's a mechanism of what we call as a timer. So each time a frame has been sent out, a timer will be start. Okay, and then because the receiver is still waiting, okay, so it will still wait and then until the timer times out. Okay, so sender would assume, okay, so frame 1 has been lost, I did not receive the ACK0, then I would need to send back again frame 1. So by this time when the frame 1 has been received, then R1 determine, okay, this is R is equal to 1 and what I receive is frame 1. Then it can send out the ACK0. By the time it send out ACK0, it change the buffer expected would be R is equal to 0. Okay, so this is the condition if it's a lost frame. Now, what will happen if ACK is lost during the transmission? Okay, you may look at this on frame 1. Okay, frame 1 has been sent out and then timeout is started. Timer is started. So when receiver receive and then it check, oh, okay, I need frame 1 and what I receive is frame 1. So it would expect that we will send out ACK0 and expect frame 0. Okay, but ACK0 is lost. So by the time the timer's time out, the sender would receive back again frame 1. Okay, it will send frame 1, and then when the receiver check, what it expect is a frame 0, because R is equal to 0, so this is what it expect. So when it receive the frame 1, it would discard that frame. Okay, it would discard that frame and then send back again acknowledge 0. By this time, ACK0 successfully received by the sender. Okay, what if there is a delay on the acknowledgement? So if there is a delay of acknowledgement, we consider it as a loss also, not loss, because we have a timer. Okay, so for example, frame 0 successfully received by the receiver because it expect R is equal to 0. So it will send out ACK1, right? Now, because it's waiting for the acknowledgement. Okay, and then before the acknowledgement has been received, it's timeout. Okay, so what the sender do is that it would send out frame 0 again. And then ACK1 has been received. Okay, ACK1 has been received after the sender send out the S is equal to 0, frame 0. So, the timer will be reset. Okay, they would reset the timer. Okay, and in this case, they would send out frame 1. At the same time, when the receiver received the frame 0 and then it checked on the buffer, what it expect is a frame 1, but what it received is a frame 0. So the receiver would discard this frame. Okay, and then send back again ACK1. Okay, so when it received the ACK1, sender would discard it. Okay, sender would discard because of it already sent out the frame 1. So what it expect is ACK0. Okay, now frame 1 lost. And then there's a timeout. So what happened is that it would send back again frame 1. Okay, so at this time, the receiver did not receive yet again, right? Frame 1, and it expect a frame 1. Then, so it will pick up that frame 1 and then send out the ACK0, Okay, piggybacking. So using this previous stop and wait ARQ, it's like you need to send first and then receive the acknowledgement. There's a lot of delay or wasting time of the resources. Okay, because sender can become a receiver and receiver can become a sender. So they combine the data frame with the acknowledgement, and each of them would set up two different buffers, one as a receiver and then one as a sender, each of these hosts. Okay, so this is what we call as piggybacking. Okay, so in this case, let's say it's reset. So A send first. A will send first frame 0, acknowledgement 0, and then when B receive it, okay, receiver should be R is equal to 0, right? So because R is equal to 0, which is the same as what it expect, it will send out ACK1. Okay, because it received acknowledgement 0, then it would send out frame 0. Okay, S is equal 0, right? So it will send out frame 0 to the A. So here, R is equal to 0. And then what it received is a frame 0. And then when A check, it received an acknowledgement 1. Okay, so it would send out frame 1 with acknowledgement 1. Just like that. So piggybacking use this type of style to maximize the resources, okay, in the network. Okay, now go back and ARQ. The go back and ARQ has several features. Okay, it's because of using the stop and wait ARQ is something like you just can only send one frame at one time. But for go back and ARQ, they they plan to send out multiple frame, okay, multiple frame or packets to the receiver, okay, so that the processing would be much more effective. So in this case, if they want to send out multiple frame, then they need a sequence number and also buffer. So the sender and receiver buffer is built up, okay, like a sliding window. And then they also have a control variables and timers and type of acknowledgement needed. Okay, and then what would be the resending frame and the operation. So the sequence number, the frames are numbered sequentially. Okay, so that if the sequence is collected, then it would send up to the upper layer, okay, and be processed after that. So to create numbers, okay, they may need to have what is the maximum frame for the sender and receiver, okay, and then the sequence numbers range from 0 to 2m minus 1, okay, 2m minus 1. So if m is equal to 3, so if m is equal to 3, where is my pen? Hold on. Okay, now, if m is equal to 3, so how many frames that we can have in the sliding window is that 2 times m minus 1. Okay, so from 0 to 2 minus m, 2 times m is minus 1, which is 0 to 7. Okay, so 2 times 3, sorry. This is not supposed to be 2 times m. It's supposed to be power. Like that. 2 power of m minus 1. So 2 power of 3 is 8. 8 minus 1 is 7. Okay. So your sequence would start at 0, 1, 2, 3, 4, 5, 6, 7, and then repeat back again that sequence. Okay. Now, this is what it looks like for the sender sliding window, because we have the size of the window is 7. Okay. Sorry. The sequence is 7. Then the window size, okay, is also the same thing. So we start at 0, 1, 2, 3, 4, 5, 6, 7, 6. So the window size is less than that. So 2 power of 3 minus 1. Okay, so the window size should be, where is the line? Susah betul nak cari. Okay. Hold on. Okay. Where is my pen? Hold on. Okay. Pen. Now, so the size of the sliding window here is 7, comes from 2 power of m minus 1. So please note that the size of the sliding window, okay, window is equal to 2 power of m minus 1. Okay, but the sequence start at 0 until 7. Okay, so this is before the sliding. Okay, and then after the sender send out packet 0 and packet 1, okay, then the window slide 2 frames next to it. Okay, so this is what's the functions of the sliding window. And then whereas for the receiver, because this is a go back and the size is only 1. Okay, as you can see, this is the sliding receiver sliding window. So R is equal to something. So this is what it expect to receive. Okay, so this is before the sliding. And then after it receive frame 0, then it will slide the next one. Okay, so here what it expect is, R is equal to 1. So it will expect sender to send out frame 1. Now, the control variables, okay, for this go back and right, it does have three variables on each of them, okay, on the sender. Okay, look at this one, S here is holding the sequence number of the recently sent out. Means that what is the sequence number frame that we have recently sent, the current one. Okay, and then SF here, okay, holds the sequence number of the first frame of the window. And then SL here holds the sequence number of the last frame in the window. As for the receiver, it holds the sequence number of the frame it expects to receive. Okay, and then look at this figure on the sender window. The frame that has been acknowledged, okay, means that the acknowledge has been received, right? So the sliding window would move to the next. Okay, it will not stay after it has been acknowledged. And then after, okay, the sender window, this part is what we call as the frame that is waiting to be sent out. Okay. Also the same on the receiver window. After the frame has been received and acknowledged, it will be moved out. Okay. It will be moved out and then pull up to the upper layer. Okay. And then usually the next one, the next frame that cannot be accepted, okay, would need to be stay, okay, before after the receiver here. Okay, so this side is the frame that cannot be accepted. Okay, so next is that normal operation. Now see that, where is my pen? Okay. Okay, so in this case, okay, the size of the sliding window is 3, right? Okay, so means that the sequence is 0, 1, 2, 3. So as you can see, so the m is equal to 2. So the sequence should be 2 power of m by minus 1. Okay, would be 3, as the size of the sliding window. But the sequence should start from 0, 1, 2, 3. I'm missing one here. Sorry. Okay, 0, 1, 2, 3. Okay. Now, this is the size 3 frames on the sliding windows. And then let's say we start at 0. So the start frame is 0. And then only the frame 0 has been sent out. Okay. And then the last frame need to be waiting to that we want to send is 2. So first frame, they would send out first frame 0. Okay. So when it received the frame 0, R is on 0. So when it received frame 0 here, okay, then 0 will be pulled up, okay, sent out to the above. And then it would slide to the next one, this one, okay. So after that, after frame 0 has been sent out, sender just send frame 1. And after it received frame 0, receiver receive frame 1. Okay, so at this time it should send out for acknowledgement for the frame 0, right? But at this time it already received the frame 1. So in this case, it would send out ACK2. So what does it mean? If the receiver sent ACK2, okay, and the sender received this ACK2, so it knows that frame 0 and frame 1 has successfully received. Okay, and it is waiting for frame 2. So in this case, okay, when the sender send frame 1, so S is equal to 1 here. Okay, S is equal to 1. And then when it received the ACK2, it knows, okay, 0 and 1 has been acknowledged. So it would slide the window to 2, frame 2. Now S is on 2, and then it will send out, okay, it will send out frame 2. Okay, so at this time, the receiver received 2, so it will send ACK 3. So when the sender receive acknowledgement 3, then it would slide the window to frame 3 and send frame 3. Okay, so go back and means that the purpose of using this go back end is that to be able to send out multiple frames. So in this case, one of the example is this one, frame 0 and frame 1. Okay, what happened if it's lost? Now, if it's lost, for example, in this case, receiver receive frame 1, and then it would send out ACK2. Okay, so ACK2 has been successfully received, and then the window slide to frame 2, and it sent out the frame 2. So receiver slide to the frame 2 here, and then it was waiting for frame 2. At the same time, sender would send out frame 3. Okay, sender would send out frame 3 here. So S is equal to 3. Alright. When it receive frame 3, what the receiver expect is frame 2. And then frame 3 is supposed not to be received. It's not in the window of the R. So they would be discarded. So they would not explain or inform to the sender. But because each of these frame has been sent out, the timer will start. Okay, after the acknowledgement has been received, they will start again the new timer. So frame 2 has been timed out, and because it did not receive any acknowledgement. So because no acknowledgement and timeout happened, it resend again 2, frame 2 here. So S is equal to 2. Okay, so and then it would send out. Okay, at this time it received the frame 2, which is correct. So it slide to R is equal to 3 and send out ACK 3. So again, because frame 3 has been discarded, it needs to send out or resend back again frame 3. So then it slide to S is equal to 3. So this is what happened if it's lost. Now, the meaning of the go back end here, because of it would go back or resend to the point before it start. Okay, and here is on the SF, which frame has been started that they have start to send and did not receive the acknowledgement. So because they did not receive acknowledgement on F here, okay, on this SF, so because frame 2 has not been received, and then they have to go back to the frame 2 and then resend back again. Okay, so that's what it means the go back end. Okay, next, sender window size. I did mention before, the size of the window is 2 power of m minus 1, right? And then, but the sequence start at 0 until 2 power of m minus 1. Okay, so why do we need to do that? Okay, look at this figure. Okay, because we use this method, the size is 2 power of m minus 1, but the sequence must start from 0 to 2 power of m minus 1. So means that the sequence is 0, 1, 2, 3, but the size is 3. Okay, so at the window here, when it sends frame 0, and then the acknowledgement is lost. Okay, R move to the next one. And then at the same time, S is equal to 1. So they send out frame 1. Also, the acknowledgement is lost. But the R move. Okay, R move to 1. And then next, after it received frame 2, it also received the frame. And then send out the acknowledgement. But the acknowledgement is lost. So at this time, the frame does not move because no acknowledgement received. Okay, so and then the timeout happened. So when the timeout happened, it would send back again to the first frame that does not receive the acknowledgement. Okay, so this one, so it will send back again the frame 0. Okay, but at this time, R is equal to 3. They expect frame 3, but what they receive is frame 0. So it would be discarded. Okay, it will be discarded. So because they discard it, they maintain the correctness of the sequence number. Okay, now you look at the right side here. Ada punya pen. Okay. Oh, sorry. Okay. Now, let's say we use the same size or we use the window size to... kenapa ni? Hold on. Okay, now, what will happen if we use the size of windows 2 power of m? Hold on, sorry. Okay. Now, if what would happen if we use a 2 power of m instead of 2 power of m minus 1, So, if the size is 2 power of m minus 1, we can correctly discard it. But let's say we make the size the same as the numbers, okay, 2 power of m, Now, the sequence, okay, the size will become 4, and then sequence will be 0, 1, 2, 3. So what will happen is that they will send out frame 0, and then the acknowledgement loss, frame 1, ACK loss, frame 2, ACK loss, and then frame 3, S is equal to 3, and then ACK loss. And then at this time, when it receive frame 3, it moves to the next slide, and they slide to the next frame, which is R is equal to 0. And then at this time, because they did not receive the acknowledgement for frame 0, it would restart back again to the first frame that did not receive the acknowledgement. So S is equal to 0. So they resend back again the frame 0. At this time, the R is equal to 0, right? But it expects the next frame. So what happened is that it erroneously accepted that frame. So that's why the size of the sender window must be less than 2 power of m. Please correct that part. And then the size of the receiver window is always 1. Okay. Now, hold on. Let me have a drink first. Right. Sorry. Now, the next ARQ is an improvement of the go back end. Where we use the sender and receiver windows, okay, use a negative acknowledgement operation, sender window size by directional transmission and pipelining. Okay, the features or the sizes is much more smaller compared to go back end. Okay, but they use the same size. Okay, they use the same size. So in this case, if the sender size frame is 2, then the receiver also use 2, like that. Okay, so they use the same how to say, they use the same variables, okay, variables that to refer, okay, to refer to the frames itself. But for sender, they have 3 variables. One is SF, S, and SL. As for the receiver, they have RF and RL. Okay, and then those frame that has been acknowledged, they would slide to the one frames that is needed to be sent out. And then those outside of the frame of the sliding windows is what we call as the frame waiting to be sent. Okay, the same thing is for the receiver. Okay, the frame that has been received and acknowledged will be phased out, and then they move the sliding windows. And then the yellow color here is the frames that cannot be accepted, means that it should be dropped. All right. Now, for a selective repeat ARQ, because of the size of the windows, in this case, they use they use the size of 2 power of m divide by 2. Okay, 2 power of m divided by 2. Okay, so I didn't mention it because you can just read this because this is part of the degree. Okay, so 2 power of m divided by 2 because remember, okay, so here is 1, 2, 3, 4. Okay, the sequence start from 0 to 3 means that m is equal to 2. Okay, m is equal to 2 means that the sequence start from 0, 1, 2, 3. So the size would be 2 power of m or 2 power of 2 is 4. 4 divided by 2 is 2. So this would be the size of the window for both sender and receiver. Okay, so let's say that's a lost frame. Okay, so sender would send out, and because frame 0 and 1 is in between the sliding window, so first they send out the frame 0. So the receiver received this. Okay, receiver received this, and then sender send frame 1. So when the receiver check, oh, okay, I have received frame 0 and then I have received frame 1, then I can send out ECK2. Okay, so the window would slide to the next one, which would be receiver will be on this side. Okay, this one, okay, now when the sender receive ACK2, so means that the receiver expect frame 2 to be sent out. So means that this has been acknowledged, this has been acknowledged. So they slide to the next one, which is frame 2. So S is equal to 2, and then it send out frame 2. But frame 2 is lost. At the same time, sender send out frame 3. It's because of this is in between the sliding. So when they send out the frame 3, the receiver receive the frame 2. Okay? Sorry, frame 3. So they receive the frame 3. Most of the time they color it gray to show that the frame that has been received is not in sequence but successfully received. Okay, and then after that, because they are still waiting for frame 2, it would send out because it already received the frame 3. Yeah, so they would need frame 2, so it will send negative acknowledgement 2. Okay, negative acknowledgement 2 to the receiver. So when the sender received the NAK2, it would send out the frame 2, resend back again. They would resend back again the frame 2. So in this case, the both frame 2 and frame 3 has been successfully received. So they would be moved up to the next layer. And receiver sliding window would move to the next frame. Okay, so that is for the selective repeat. It is much more better compared to the go back end because of the receiver size of the go back end is only 1, right? But then if there is like the next frame, like frame 3 that has been received earlier, it need to be discarded, which is a waste. So that's why they come up with this type of mechanism. Okay, so that's it for the data flow control. Okay, so next would be mana pula ni? Hilang pula. Okay, hold on. Hold on, I cannot see my my sliding window. Okay. Okay. Yeah. Now I can share. Suppose. All right. I hope you can see this. Okay. Error corrections and control. 8:16. I hope I can finish this. And then next slide, I'll continue on the next week. Okay, now This would be chapter 4. As I have mentioned before, layer 2. Layer 2, part of the services that it should provide is that error correction and control. So, I would introduce the type of errors, error detections, and error corrections. Okay. All right. Network must be able to transfer data from one device to another with acceptable accuracy. So a system must guarantee that the data received are identical to the data transmitted. So anytime data are transmitted from one node to the next, they can become corrupted in the passage because of the interference, noise, and attenuation. So there are many factors that can alter one or more bits of a message. So some applications require a mechanism for detecting and correcting errors. Some applications can tolerate a small level of error. For example, random errors in audio or video transmission may be tolerable. Okay, you can imagine that in a voice, sometimes we did miss, but we can still catch up the gist of the message. Okay, and also in a video transmission, because it represent into a bits, the color is represent into a bits. A missing colors, a one bit can be tolerable, but if we transfer text, we would expect a very high level of accuracy. So at the data link layer, if a frame is corrupted between the two nodes, it will need to be corrected before it continues its journey to other nodes. However, most link layer protocols simply discard the frame and let the upper layer protocol handle the retransmission of the frame. Some multimedia applications, however, try to correct the corrupted frame. So, in essence, data can be corrupted during the transmission, and some applications require that error be detected and corrected. Okay, so there are two types of errors. Whenever the bits flow from one point to another, they are subject to unpredictable changes because of the interference. And this interference can change the shape of the signal. So two types of errors that we have, which is single bit error and burst error. Single bit error means only one bit of a given data unit, such as a byte, character, or packet, is changed from 1 to 0 or from 0 to 1. So look at the figure A here. And then in a burst error means that two or more bits in the data unit have changed from 1 to 0 or 0 to 1. Okay? So a burst error is more likely to occur than a single bit error because, sorry, the duration of the noise signal is normally longer than the duration of one bit, which means that when noise affects data, it affects a set of bits. It's much more naturally will occur because of the transmission is too fast. It was transmitting several bits, right? So when the noise affect that bits, it usually affects the several bits of it. So the number of bits affected depends on the data rate and duration of the noise. For example, if you are sending data at 1 kilobit per second, so a noise of 1 over 100 second can affect the 10 bits. Okay? And then if we are sending data at 1 megabit per second, the same noise can affect 10,000 bits. Okay? So the durations is this one, hold on. Cannot write it. Okay, this one. Okay. All right. So 1,000 bit per seconds affected by a noise of 1 over 100. So means that it's a 10 bits. But imagine that if we have 1 megabit per second, no, actually we have 1 gigabit per second. So even if it's a 1 megabit per second, okay, so means that 1, 1, 2, 3, 1, 2, 3. And then what does it affect with a 1/100 seconds is that it affects 10,000 bits. And then what will happen if it's a 1 gigabits? Okay, so it's more than that. So how do we solve it? How do we solve it? They use the concept in detecting or correcting errors using a redundancy. So to be able to detect or correct errors, we need to send some extra bits with our data. So along with the original data, we also send an extra bits to send to the receiver to check if there's an error. So these redundant bits are added by the sender and removed by the receiver. And their presence allows the receiver to detect or correct the corrupted bits. Okay, what are the differences between the detection and correction? For detection, the correction of error is more difficult than the detection because of they need to determine. You need to determine in error correction, we need to know the exact number of bits that are corrupted and more importantly, their location in the message. And then in error detection, we are only looking to see if any error has occurred or if there is any error on that a group of bits. So the answer is a simple yes or no. Okay. And then for a single bit error is the same for us as a burst error. Okay. So in error corrections, the number of errors and the size of the message are important factors. If we need to correct a single error in an 8-bit data unit, then we need to consider 8 possible error locations. But if we need to correct 2 errors in a data unit of the same size, then we need to consider 28, where it's a permutation of 8 by 2 possibilities. So you can imagine the receiver's difficulty in finding 10 errors in the data unit of 1000 bits. So there are two methods of error corrections. One is a forward error correction where it's a process in which the receiver tries to guess the message by using the redundant bits. This is possible as we see later if the number of errors is small, or correction by retransmission, where it's a technique in which the receiver detects the occurrence of an error and then asks the sender to resend the message like a negative acknowledgement, NAK. So resending is repeated until a message arrives that the receiver believes it's error-free. Usually, not all errors can be detected. Okay, we do remember about the ARQ, right? So it's a method of an handshaking. So when the sender receives, it would expect an acknowledgement, and then after it received the acknowledgement, then it can send out the next frame. So let's say if there's a loss, okay, so they would not know, okay, there is a loss there until it have some indicators such as the timeout. Okay, as for this is like an ideal one. Okay, so coding, the redundancy is achieved through various coding schemes. We call it as a coding, not like a programming, like a certain encoding schemes. So in this case, the sender adds redundant bits through a process that creates a relationship between the redundant bits and the actual data bits. And then the receiver checks the relationship between these two sets of bits to detect errors. The ratio of redundant bits to data bits and the robustness of the process are important factors in any coding scheme. So coding schemes can be divided into two broad categories: block coding and convolution coding. Okay, in a block coding, the message is divided into blocks, which each k bits, okay, k size bit is what we call as the data words, the original words. We term it as a data words, and then we would add r size redundant bits to each block to make the length as n is equal to k plus r. So, and then the resulting n-bit blocks are what we call as the code word because it contains data words and the redundant bits. It is important to know that we have a set of data words, each of size k, and a set of code words, each of size of n. With k bits, we can create a combination of 2 power of k. This is a mistake. Hold on. Should be 2 power of k. So 2 power of k data words with n bits, we can create a combination of 2 power of n code words. Okay. So since n is bigger than k, the number of possible code words is larger than the number of possible data words. So the block coding process is 1-to-1. The same data word is always encoded as the same code word. Okay. So this means that we have 2 power of n minus 2 power of k code words that are not used. Power This one is power, this one is power. So because n is bigger, and then we have several code words that are not used. So we call these code words as invalid or illegal. Okay, so the trick in error detection is the existence of these invalid codes. So if the receiver received an invalid code word, this indicates that the data was corrupted during the transmission. For example, remember about the block coding in the data transmission, digital data transmission, right? Remember? So I have introduced about the 4B or 4B/5B block coding. So this is one of the coding schemes that k is equal to 4 and then n is equal to 5. So as we saw it, we have 2 power of k, which is 16 data words, and 2 power of n, which is equal to 32 code words. So what we saw is that 16 out of 32 code words are used for message transfer, and the rest are either used for other purposes or unused. So how can errors be detected by using block coding? So if the following two conditions are met, the receiver can detect a change in the original code word. One, the first condition is that the receiver has or can find a list of valid code words. So if there is a valid code words in the table, then it is accepted. Okay, the code word will be accepted. Or if there is a condition that the original code word has changed to an invalid one. So if the receiver detect that the code word received is an invalid, then it would not accept that code word. Okay, so this is a process of error detection in block coding. So the sender would encode this data word and generate the redundant bit to become a code word. Okay, so generate the R bit. So the sender creates code word out of data words by using a generator that applies the rules and procedures of encoding. And then this code word would send to the receiver and may be changed during the transmission. So if the received code word here is the same as one of the valid code words, so the word is accepted. So they will check. Okay, they will check the code word, okay, and then extract it, okay. So if there is no changes, and then what it received is a valid code word, it will be accepted by extracting the data word. Okay, they will extract the data word for use. But if the received code word is not valid, it will be discarded. However, if the code word is corrupted during transmission, but the received word is still match a valid code word, then that's the condition that what we call as undetected error. Okay. Now, example. Let us assume k is equal to 2 and n is equal to 3. Okay, means that data word is 2 bit, code word is 3 bits. So the table shows the list of data words and code words. Later, we will see how to derive a code word from a data word. Okay, assume the sender encodes the data word 01 as 011. So this is from the sender side. So they will encode to become 011 here. Okay, consider the following cases. The receiver received 011. So if it's a 011, it will check back again on the table of code word. It is a valid code word. So the receiver extract 01 from it. The code word is corrupted during the transmission and 111 is received. Okay, so the leftmost bit is corrupted, this one. So this is not a valid because when you check, it only 000, 011, 101, and 110. So there is no 111, which is invalid. So because it is invalid, it will be discarded. The third scenario is that the code word is corrupted during the transmission. It's supposed to be 011, but now the receiver receives 000, which means the right two bits are corrupted. So when the receiver check, it is valid code. So this is a valid code. The receiver incorrectly extract the data word 00. So the two corrupted bits have made the error undetectable. Okay, so undetectable error. So what would the next part would be error correction. So error correction is much more difficult than the error detections. In error detections, the receiver needs to know only that the received code word is invalid. But in error correction, the receiver needs to find or guess the original code sent. Okay. Now, we need more redundant bits for error corrections than for error detections. So the figure shows the role of block coding in error corrections. We can see that the idea is the same as error detection, but the checker functions are much more complex. Okay. Here, it will generate more bits for the redundant bits. And then when it need to check, okay, it will need to check if there's an error and to predict or to try to correct the bits. Okay, for example, and the structure of encoder and decoder in an error correction is that let us add more redundant bits to the previous one. So in this case, the data word is 2 bits, but the code word error added, okay, means that the redundant bit added is 3. So example to see if the receiver can correct an error without knowing what was actually sent. So we add 3 redundant bits to the 2-bit data word to make 5-bit code words. Again, later we will show how we choose the redundant bits. For the moment, let us concentrate on the error correction concept. So this is the table that we refer to. And then assume the data word is 01, this one. So the sender consults the table to create a code word 01011. So the code word is corrupted during the transmission. And then what it received is 01001, which means there's an error bit on this part. This part. The second bit from the right. Okay, this one, bit 0 here. It's supposed to be bit 1. First, the receiver finds that it looks at the code word. So 01001. There is no 01001 on the code word. So what it received is not in the table, which means there's an error occurred. So detection must come first before the corrections. And then the receiver, assuming that there is only 1 bit corrupted, it will use the following strategy to guess the correct data words. So the strategy is using Hamming distance. One of the central concepts in coding for error control is the idea of the Hamming distance. Hamming distance is between 2 words of the same size is the number of differences between the corresponding bits. We may wonder why Hamming distance is important for error detections. The reason is that Hamming distance between the received code word and the send code word is the number of bits that are corrupted during the transmission. For example, if the code word 000 is sent and then 01101 is received, okay, 3 bits are in error. Okay, these 3 bits, 111 is an error, and the Hamming distance between these two is 3. Okay, Hamming distance is for this is 3. So in other words, if Hamming distance between the send and receive code word is not 0, so the code word has been corrupted during the transmission. Hamming distance can easily be found if we apply the XOR operation on the two words and count the number of ones in the result. Note that Hamming distance is a value greater than or equal to 0. Okay, so to calculate the Hamming distance is that the value should be is greater than or equal to 0. Okay, so there's no negative number. So the Hamming distance between two words is the number of differences between corresponding bits. For example, find the Hamming distance between two pairs of words. So the Hamming distance between these two words is xy. So Hamming distance between 000 and 011 is 2 because when you XOR 000 and 011, you XOR the in-between bits. So the first bit is 0, XOR with 0. Okay, so you will get 0. Okay, remember the logic operation of XOR. If it's a 0 and 0, you will get 0. If it's a 1 and 1, okay, XOR with 1, it's also 0. But if there's a different input, for example, 0 and 1 or 1 or 0, okay, when you XOR it, you will get 1. So in this case, 0 XOR 1 is 1, 0 XOR 1 is 1. So in this case, there are 2 bits 1 here, so the Hamming distance is 2 because there are 2 bit 1. Okay, another example is 10101. Okay, and then there's a changes bit happen on 11110. This is the one that has been received. So when you XOR it, okay, 11 is 0, 0 XOR 1 is 1, 1 XOR 1 is 0, and then 0 XOR 1 is 1, and then 1 XOR 0 is 1. So what happened is that there are 1, 2, 3 bits 1. So the Hamming distance is 3. Okay, so this is just to calculate the Hamming distance for error detection. Now, let me check. Okay, I have 20 minutes. In a set of code words, the minimum Hamming distance is the smallest Hamming distance between all possible pairs of code words. So let's say if S errors occur during the transmission. So the Hamming distance between the send code word and receive code word is S. If our system is to detect up to S errors, so the minimum distance between the valid codes must be S plus 1. So that receive code word does not match a valid code word. So in other words, if a minimum distance between all valid code words is S plus 1, then the receive code words cannot be wrongly mistaken for another code word. Then the error will be detected. So although we said that the minimum distance is S plus 1, may be able to guarantee more than S errors in some special cases, only S or fewer errors are guaranteed to be detected, not S plus 1. So, what is the minimum Hamming distance for this coding scheme? So, this is a table of data words and code words that we can refer. So, we need to find all Hamming distance here. If it's a 000 and then what you receive is 011, so when you XOR it, you would get 2 bit 1 and then 000 and then 101. Okay, Hamming distance is 2. 0, 0, 0, 1, 1, 0, also 2, 0, 1, 1, and then 1, 0, 1. Here, okay, the possibility is that, okay, 0, 1, 1, and then 1, 0, 1 is that 0, 1 is 1, and then 1, 0 is also 1, 1, 1 is 0. So distance is 2. And then 0, 1, 1 and 1, 1, 0 also would produce two big one. Okay, because the middle one here is 1 and 1. Okay, would produce 0. And then 1, 0, 1, and then 1, 1, 0. Okay, the Hamming distance, okay, the Hamming distance would be 1 and 1 is 0, 0 and 1 is 1, 1 and 0 is 1. So there are two big ones in these cases. So the minimum distance that we can detect, minimum Hamming distance for the error detections is 2. Okay, what if we have 5-bit code words, but the data word is 2, Okay, so in this case, 0, 0, 0, 0, and then 0, 1, 0, 1, 1. Okay. Now, when we detect it, okay, so the changes happen is that 1 is here, okay, that's a change, 1 is here, and then bit 1 is here, 0 and 1, and then 0 and 1. Okay, the rest is the same, so the distance is 3. And then 1, 0, 1, 0, 1 for these cases, if we receive that, so the minimum distance would be 3 because there are 3-bit 1. And then if it's a 1, 1, 1, 1, 0, so the minimum distance would be 4. Okay, next, 0, 1, 0, 1, 1. So the possibility that we receive 1, 0, 1, 0, 1, so the distance, Hamming distance should be 0, 1 is 1, 1, 0 is 1, 2, 0, 1 is 1 also, 3 bits, and then 1, 0 is 4 bits, and then 1, 1 is 0. So Hamming distance would be 4. And then 0, 1, 0, 1, 1. Okay, 0, 1, 0, 1, 1. And then if we receive 1, 1, 1, 1, 0. So here 1, 1, 1, 0. The Hamming distance should be 0, 1 is 1 bit, 1, 1 is 0, 0, 1 is 1 bit, which is 2. And then 1, 1 is 0, 1, 0 is 1. So 3 bits 1. And then 1, 0, 1, 0, 1. If there's a possibility that it receive 1, 1, 1, 0. So what will be the Hamming distance? It will be 1, 1 is 0. 0, 1 is 1. 1, 1 is 0. So only 1 bit at currently. And then 0, 1 is 1. So there are 2 bits. 1, 0, it's also 1. So there are 3 bits 1. So the minimum Hamming distance for this case, for these types of code words, it would be 3. The smallest that it can do some error corrections. Okay. Almost all block codes used today belong to a subset of block codes called linear block codes. So the use of non-linear block codes for error detection and correction is not as widespread because their structure makes theoretical analysis and implementation difficult. For our purposes, a linear block code is a code in which the exclusive OR, okay, or addition modular 2 of 2 valid code words creates another valid code words. Okay, so the minimum Hamming distance is the number of 1 in the non-zero valid code word with the smallest number of ones. For example, in our first codes, the number of ones in the non-zero code word, and this is a zero code words. The next one here, okay. The number of ones in the non-zero code word is 2, 2, and 2. Okay, so 2, 2, and 2. Um, uh, here, if you can see that 01011, okay, so the number of non-zero code words would be, minimum distance would be 2, Okay, so the minimum Hamming distance is 2 in the linear block codes. Now, how do we need to detect, okay, the position of the bits that we need to detect which bit have that error. So we can use a parity check. Perhaps the most familiar error detecting code is the parity check code, or what we call as a linear block code. In this case, a k-bit data word is changed to an n-bit code word where n is equal to k plus 1. So the extra bit is what we call as the parity bit. It's selected to make the total number of 1 in the code word even. So that is what we call as a even parity bit. In some cases, they implement odd number 1 where it is called as a odd parity bit. Okay. So but for this topic, we discuss the even case first, okay? So the minimum Hamming distance for this category is 2, which means that the code is a single bit error detecting code. So our first code is a parity check code. K is equal to 2 and then N is equal to 3. So the code table is also a parity check code with K is equal to 4 and N is equal to 5. Okay, so for a simple parity check code, if the data word is 4 bits, then the 5th bit here will be added as a parity bit. Okay, because this is an even, then they will count out how many bit one here. So because there is no bit for 000, so they will just add bit 0 as the parity bit. But then if it's a data word 001, then to make it even, they need to add parity bit 1. Okay. And then this one 0010, this is they have 1 bit 1. So they need to make it even. So parity bit will become 1. So the rest will be the same. Okay. Now, figure shows a possible structure of an encoder at the sender and a decoder at the receiver. Now, let's say they receive the data words and then they will calculate how many bit one. How many bit one on this data word, and then they will generate the parity bit. So attached together with the data word, then now it will become a code word. When it's sent to the receiver, okay, the receiver would add together. They will check. They will check each bit, including the parity bit. Okay. So when they check it, if it's not even, okay, if the syndrome is not 0, if the syndrome is not 0, if it's even, it will produce 0. But if it's not 0, then it means there's a 1 bit that is affected. Okay, it's an odd, so it would discard it. Okay, the decision logic is that it will discard it. But if syndrome is equal to 0, then the data word will be accepted. They remove the Q0 here, the parity bit. So what's left is only the data word. Okay, so that's all for the corrections. No, for parity check. Okay, for the parity check and the corrections. Okay, for this chapter. Okay, so and then next. Okay, that's end of it. Allah, how to end it? Okay, discard dulu. Okay. So is there any questions in on the slides? Is there any questions? I will upload the notes later on. No. Notes has been uploaded. Yes. I would just need to upload the lecture later on. Okay, so for the next chapter would be this one. Okay, we have covered the error corrections and control previously. Okay, we have finished this error correction and control. Now what's left is this one. No boy. Hold on. Ash. This one. Okay, Ethernet LAN, fast Ethernet, gigabit Ethernet, and ATM. So that's what we need to cover up later on. Sorry. I did not share my screen. Hold on. This one, So the next chapter later on would be this chapter about network access, or in this case protocol Ethernet. Okay, I will explain it later on. I'll see you next about this chapter. Okay, so this is still chapter 2. No, layer 2. Because Ethernet is a protocol that operate on data link layer. Okay, so so no chat. Okay, no questions. Okay, so I'll end this session. And I'll see you next week. Okay, so that's all. Thank you and good night. Okay, bye. Assalamualaikum.
وعليكم
وعليكم
السلام.
السلام. Thank you, Doctor.
وعليكم
Thank you,
السلام.
Doctor.